In this lecture, we're going to take a careful look at the kinds of procedures we can build. We'll first go back to look very carefully at the substitution model to see how the rules for evaluation help us determine the evolution of a process controlled by a procedure. We will then see how different kinds of process evolution can occur, with different demands in terms of computational resources. And we will see how to characterize those differences formally in terms of something called an order of growth of a process. Finally, we will explore examples of procedures from different classes of growth, helping you to begin to relate how choices in procedure design may affect performance of the actual use of the procedure. Now that we've seen two different implementations, two different procedures for the same problem, a recursive one and an iterative one, we need a way of characterizing why that difference occurs. And to do that, we're going to go back to our substitution model and use a slightly different viewpoint on it. In particular, we're going to look at the substitution model as a set of rewrite rules. That is, a set of rules that says, given an expression of a particular form, here's how to rewrite that expression into a different form. So for elementary expressions, basically they're just left alone. That is, if we have a number, an initial name for a primitive procedure, or a lambda expression that's naming a procedure, we simply leave the expression exactly as it is. If our expression is a name that was created by a define, then we'll rewrite the name as the value it has associated with it by the definition. The special form if we'll write using the rules we've seen. We'll evaluate the predicate. If it terminates in a non-false value, then we'll rewrite the entire if expression as the value of the consequent. Otherwise, we'll rewrite it as the value of the alternative. And finally, combinations. We use the rule that we first evaluate the operator expression to get the procedure, and we evaluate the operands to get the set of arguments. If we have a primitive procedure, we're going to do just the right thing. Otherwise, we're going to replace this entire expression with the body of the compound procedure with the substitution of the parameters and the arguments as appropriate. Given that model, we can now try and capture more formally how different processes evolve in different ways. And we use an idea called orders of growth. This is intended to be a way of measuring how much of a particular resource a process is going to take as it goes through its evolution. And typically the resources we're interested in is how much time will it take and how much space will it take. What we're going to do is be a little bit formal here as follows. Let's let n be a parameter that measures the size of the problem we're interested in. In the case of factorial, n will be simply the size of the argument. We're going to let r of n be a term that denotes the amount of resources we need to compute a procedure of size n, and that's what we want to try and get a handle on. Typically, we're interested in how r of n behaves for really large values of n, in the asymptotic limit. We say that r of n, that particular expression for the amount of resources we need, we say it has order of growth theta of f of n. If we can find a function f of n such that r of n is basically of the same order as f of n. And more formally, we say if we can find two constants, that is, things that don't depend on n, such that k1 times f of n is less than or equal to r of n, is less than or equal to k2 times f of n, when n gets really large. I know this is a lot of math. We're going to make it clear in a second when we look at some examples, but that's the formal definition we're interested in. As we said, what we're going to do in terms of resources are typically measure space, and that really comes down to counting up how many deferred operations there are and trying to estimate how that changes as n changes. And the second one is time, here measured by the number of primitive steps we have to go through. And again, we're going to try and estimate how many of those we need as a function of the size of the argument. So now let's combine that idea of treating the substitution model as a set of rewrite rules and this idea of trying to characterize the growth of the procedure to look at our two examples. Here's fact once more. And here's a partial trace of fact using those rewrite rules. We start with fact 4. Substituting in reduces to an evaluation of an if. Since the predicate is not true, that reduces to taking the alternative, which is that next line. And we keep doing this. Key thing to notice are the orange colored lines. Those show the results of the evolution of this process. Fact 4 reduces to a deferred operation of times 4 and fact 3, which reduces again. And notice the shape of this process. It grows out and then shrinks back down once we get down to the base case. In particular, we can see that the number of deferred operations grows linearly with the size of the argument. If I go from 4 to 5, I add one more deferred operation. We can also see that the number of steps is basically twice the size of the argument. I have one step to expand out and another step to contract back down. And let's compare that to the iterative factorial version. There's the procedure, the helper procedure that we're primarily going to use, and here's the trace of IFACT. We're just using those rewrite rules to substitute in. Again, IFACT helper is going to reduce to a call to if, but now the next reduction is just back to a single call to IFACT helper. Once more, look at the orange lines. Notice the different shape. No deferred operations, no growth in space. The amount of room I need to keep track of this is simply the same, no matter what size argument I use. So we see that there's constant space here. In terms of number of steps, well, there's basically 2 steps for each operation here, but that basically also comes down to being very similar to our factorial case. So we can formally characterize that. We say for fact that its order of growth in space is linear. And the reasoning we just talked about. The amount of deferred operations increases by 1 as we increase the argument by 1. So it's literally the size of the argument that determines the number of steps we have. In terms of time, we also say it's linear. Remember, the constant doesn't matter. The fact that it takes 2 steps for each increase in the size of the argument still means it grows linearly in n, where n is the size of the problem. Iterative fact we saw behave differently. Here, in terms of space, there are no deferred operations. There's nothing being stacked up. There's no growth. And we say as a consequence that it's constant in space, which we write as theta of 1, saying it does not depend on the size of the argument. Time here is also linear. It grows incrementally with a change in the argument size. The actual constant may be slightly different, but what we're interested in is the asymptotic behavior, and therefore both factorial done recursively and factorial done iteratively have a similar linear growth in time. What we can see, though, is that we can now formally characterize the difference between the 2 algorithms. One is linear both in space and time, the other is linear in time but constant in space. Let's step back for a second. The key reason for estimating orders of growth isn't just to be able to say what they are, but it's actually to let you begin to recognize how a particular design for an algorithm is going to affect what space and time you use. This will allow you to work backwards to decide how my design choices are actually going to be important as I try and put my algorithm together. And so what we're building up are templates for recognizing, in this case, linear recursive procedures and linear iterative procedures. Having seen 2 different kinds of processes, one linear and one constant, we want to fill out our repertoire of things by looking at other kinds of processes. The next one is an example of an exponential process, and it deals with a classic function called Fibonacci. Its definition is that if its argument is 0, its value is 0. If its argument is 1, its value is 1. And for all other positive integer arguments, its value is the sum of its values for the 2 preceding arguments. We would like to write a procedure to compute Fibonacci, and in particular see how it gives rise to a different kind of behavior. To solve this problem, let's use our tool of wishful thinking. Here, wishful thinking says, let's assume that given an argument n, we know how to solve Fibonacci for any smaller sized argument. Using that idea, we can then work out a solution to the problem. With this in hand, it's clear that the solution to the general problem is just to solve 2 smaller sized problems, then add the results together. Note that in this case we are using wishful thinking twice, not once, as in our previous examples. Here's a procedure that captures this idea. First, we introduce a new expression called a cond expression. Cond uses the following rules of evaluation. The cond consists of a set of clauses, each of which has within it a predicate clause and 1 or more subsequent expressions. Cond proceeds by first evaluating the predicate of the first clause, in this case the n equals 0 case. If it is true, then we evaluate in turn each of the other expressions in this clause, returning the value of the last one as the value of the whole thing. In the case of the first clause of this cond, that is the expression 0. If the predicate of the first clause is false, we move to the next clause in the cond and repeat the process. This continues for however many clauses are contained in the cond until either a true predicate is reached or we reach a clause with the special keyword else. In this latter case, that predicate is treated as true and the subsequent expressions are evaluated. Given that form for cond, we can see how our Fibonacci works. In particular, we just recursively keep solving smaller sized problems until we get to a base case. Notice that here we have 2 of them, not 1. Also notice that while this is a recursive procedure, it is different from our earlier ones. Here there are 2 recursive calls to the procedure in the body rather than just 1. Our question is whether this leads to a different kind of behavior or a different order of growth. This does in fact give rise to a different kind of behavior, which we can easily see with the illustrated diagram. To solve a problem of, say, size 4, note that we have to solve 2 problems, one of size 3 and one of size 2. Each of these requires solving 2 smaller problems, and so on. This gives rise to a kind of tree of things that we have to do, and each recursive call requires 2 smaller subproblems to be solved. This leads indeed to a different order of growth. To measure the order of growth, let's let t of n denote the number of time steps we need to solve a problem of size n. From our tree, we see that to do this, we need to solve a problem of size n minus 1 and a problem of size n minus 2. We can actually work out a detailed analysis of this relationship, but for our purposes, we can approximate this as roughly the same as solving two problems of size n minus 2. Expanding a step further, this is roughly the same as solving 4 problems of size n minus 4, and roughly the same as solving 8 problems of size n minus 6. A little math shows that in general this reduces to 2 to the power of n over 2 steps. This is an example of an exponential order of growth, and this is very different from what we saw earlier. To convince yourself of this, assume that each step takes 1 second and see how much time it would take for an exponential process as compared to a linear one as n gets large. In terms of space, our tree shows us that we have basically one deferred operation for each step, or in other words, the maximum depth of that tree is linear in the size of the problem, and the maximum depth exactly captures the maximum number of deferred operations. Let's take another quick look at how we can create procedures with different orders of growth to compute the same function. As a specific example, suppose we want to compute exponentials, such as a raised to the bth power, but to do so only using the simpler operations of multiplication and addition. How might we use the tools we've been developing so far to accomplish this? So recall the stages we use to solve problems like this. We will use some wishful thinking to assume that solutions to simpler versions of the problem exist. We will then decompose the problem into a simpler version of the same problem, plus some other simple operations, and we'll use this to construct a solution to the more general problem. And finally, we'll determine the smallest size subproblem into which we want to do decomposition. So, let's look at those 3 pieces, those 3 tools applied to the problem of exponentiation. Remember that our first stage is wishful thinking, which is our tool for using induction. It says, let's assume that some procedure, let's call it myexp, exists, so that we can use it, but that it only solves smaller versions of the same problem. Given that assumption, we can then turn to the tricky part, which is determining how to decompose the problem into a simpler version of the same problem. Well, here's one method. Notice that a to the power b mathematically is just taking b products of that factor a. But this we can also group together as a times b minus 1 products of a, and that latter we recognize as a smaller version of the same exponentiation problem. That is, we can cluster things together so that we reduce a to the bth power as just a times a to the b minus 1st power. And thus we can reduce the problem to a simpler version of the same problem, together with some simple operations, in this case, an additional multiplication. Given that idea, here's the start of our procedure for myexp. Notice how it recursively uses myexp to solve the subproblem, then multiplies the result by a to get the full solution. Of course, as stated, that procedure will fail, as it will recurse indefinitely. To stop unwinding into simpler versions of the same problem, we need to find a smallest size subproblem. Here, that's easy. Anything to the 0th power is just 1. And thus we can add our base case to our procedure, creating the same kind of procedure we saw earlier for factorial. Note how the base case will stop unwinding the computation into simpler cases and ground out this current computation. You could run the substitution model on this procedure to both verify that it works and to determine its growth pattern. However, the form is very familiar, or should be, and we can thus deduce by comparison to factorial that this procedure has linear growth in both space and time. The time is easy to see. There is one additional step for each increment in the size of the argument, and therefore it's going to take linear time to do the computation. As for space, we see that there is one deferred operation for each recursive call of the procedure. So we will stack up a linear number of such deferred operations until we get down to the base case. At that point, we can then start gathering together operations, completing the deferred multiplications, and computing out the full answer. As we saw earlier, we expect there are other ways of creating procedures to solve this same problem. With factorial, we use the idea of a table of state variables with update rules for changing the values of those variables as an alternative. We should be able to do the same thing here. So recall the idea of our table. We set up one column for each piece of information that we will need to complete a step in the computation, and we use one row for each such step. The idea here is pretty straightforward. We know that a to the bth power is just b successive multiplications by a. So we can just do the multiplication, keeping track of the product accumulated so far, and how many multiplications we have left. Thus, after one step, we will have a product of a and b minus 1 things left to do. After the next step, we will multiply our current product by a and keep track of that new result, plus the fact that we have one less thing left. And this process we can continue until we reach a point where we have no further multiplies left. Now, what are the stages of this computation?
To get the next value for the product, we take the current value of the product and the value of A, multiply together, and keep. That updates one of the state variables. To get the next value of counter, we simply subtract 1 from the current value, since we have done one more of the multiplications. That updates the other. We know that when the counter gets down to 0, there are no more multiplications to do, so we are done. And when we get there, we know the answer is sitting in the product column. And finally, we see that the starting point is just that anything to the 0th power is 1. So now we can capture this in a procedure. As with factorial, we're going to use a helper procedure to do this because we need a little more information. And as in that case, we can see that this procedure just checks for a base case, and if there, simply returns the value of prod. Otherwise, it reduces the computation to a simpler version of exactly the same computation, with a new value for prod and a new value for count, both obtained using the update rules we just created. And what is the order of growth here? In time, this is still linear, as there is one sub-computation to perform for each increment in the size of b. In space, however, we see, as we did with factorial, that here there are no deferred operations, so this is constant in terms of space. Thus, just as with factorial, we see that we can create different procedures to compute exponentiation with different classes.
So now we've seen 3 very different kinds of procedures. Something that gives rise to a constant behavior, something that gives rise to a linear behavior, something that gives rise to an exponential behavior. And those have very different costs in terms of time and space. Let's finish up by looking at a 4th kind of process that has yet another kind of behavior. Here the problem we're going to look at is how to compute exponentials. That is, to take a to the power of b, where b is an integer, but just using multiplication and addition as our basic primitive stages. As in our previous cases, the key component is to figure out how to reduce this problem to simpler versions of problems I know how to do, either simpler versions of the same problem or other operations that are more primitive. Let's start off. If b is an even integer, then a clever trick I can play is to realize that a to the power b is the same thing as taking a and squaring it, then taking that to the power of b over 2. Since b is even, b over 2 is still an integer. And the advantage of this is that in one step, I've reduced a problem in half. Well, that's okay, but what if b is odd? Well, if b is odd, I can't play the same trick, so I can simply reduce it to a simpler version of the same problem. That is, a to the power b is just a times a to the power b minus 1. Notice again, I'm using that wishful thinking idea. I've reduced this down to a simpler version of the same problem, plus some stages that I know how to do. And notice the nice thing that's happened here. Even if b is odd, in one step, I reduce it to a times a to the b minus 1. But b minus 1 is now even, so that says on the next step, I can cut this problem in half again. So either way, in a couple of steps, I'm going to be able to reduce the problem in half, and the next time around, to reduce the problem in half again. With those ideas, we can build a procedure, and here it is. It's going to take in 2 arguments, a and b, and it's going to use these cases. If b is equal to 1, we're in the base case, we're just done. Otherwise, we'll check to see if it's even, using a built-in predicate that does that. If it is, then I know that I will call fast exp again with a different version of a, now a squared, and a different exponent, b over 2. Otherwise, I'll reduce this to the product of a times fast exp of a and b minus 1, just as my rules say. Notice that this has an interesting form. In one case, it looks like it's going to behave as an iterative thing. In the other case, it looks like it's going to behave as a recursive thing. So I'm likely to have a few deferred operations, but not as many as I had before. The second and more important question is, what happens in terms of time? Because I'm cutting down the exponent in half, do I get better performance? Okay, let's measure the order of growth with a little bit of informal reasoning. We see in this case that if n is an even number, where n is the size of the problem and n is basically the size of the exponential that we're taking, then we know that in one step we reduce this to a problem of size n over 2. If n is odd, in one step we reduce it to a problem of size n minus 1, and in another step we reduce it by a factor of 2 down to a problem of size n over 2. This means in either case, after 2 steps, we've cut the problem in half. This means in 4 steps, we've cut the problem in half twice. In 6 steps, we've cut the problem in half 3 times, or 8 times if you like. And in general, in 2k steps, we've reduced the problem down to a problem of n over 2 to the k. We've reduced it by a factor of a half k times. How do we tell when we're done? Well, when we get the problem down to a problem of size 1, we're finished. And that says when n over 2 to the k is equal to 1, we're completed. And that lets us solve for k. And in fact, what we find is that k, the number of steps we're going to take, is logarithmic in the size of the problem. This is a very fast algorithm, and again, convince yourself of this by taking some values for n and comparing log of n versus 2 to the n versus n to realize that this is a very nice kind of algorithm to have. It will complete things very quickly and it'll be a much more efficient way of doing the kinds of things we'd like to do. One can actually do the same kind of reasoning, and you ought to try this to convince yourself that space is also logarithmic in the size of the problem.
To summarize, we have now seen how our substitution model helps to explain the evolution of a process that occurs when a procedure is applied. Using this model, we have seen that very different kinds of behavior can occur, even for procedures computing the same abstract function. And we saw how to characterize those differences in terms of order of growth in space and time. Already, you can see that there are different classes of algorithms. We've seen constant, linear, exponential, and logarithmic. Part of your task is to learn how to recognize the kinds of procedures that are associated with these different behaviors, and to learn how to use that knowledge in designing efficient procedures for particular problems. Let's take one more look at this idea of creating procedures to solve a problem, where the procedures can have different behaviors in terms of how their underlying process evolves. For a different example, let's look at a mathematical problem known as Pascal's triangle. The elements of Pascal's triangle are shown here. The first row just has a single element. The second row has 2, the third row has 3, and so on. And clearly there's a structure to these elements which we need to understand. So, let's structure this problem a bit. Let's order the rows and enumerate them, labeling the first row n equals 0, the second row n equals 1, and so on. We'll see that this choice of labeling leads to a cleaner description of the problem in a second. Using this labeling, we can also see that the nth row has n plus 1 elements in it. Let's use the notation p of jn to denote the jth element of the nth row. Our goal is to determine how to compute all the elements of each row. Traditionally, Pascal's triangle is constructed by noting that the first and last element of each row, except the first, is a 1. And by noting that to get any other element in a row, we add the corresponding element of the previous row and its predecessor together. If you use this rule of thumb, you can verify that this works by generating the first few rows of the triangle. So, we have an informal specification of how to generate Pascal's triangle. We can then proceed in a straightforward manner by capturing that idea in a procedure. Note the form. We have two base cases, one for when we're generating the first element of the row, and one for the last element of the row. Otherwise, we simply rely on smaller versions of the same computation to do the job. We compute the same element of the previous row and its predecessor, and then add them together to get an element of a new row. You can verify that this is correct by trying some examples, but clearly the code also just reflects the relationship we described in the previous slide. So what kind of process does this procedure engender? Well, it looks a lot like our computation of Fibonacci, and that's a pretty good clue. Just like Fibonacci, there are two recursive calls to smaller versions of the same process at each stage. In fact, a similar analysis will show that this is a process that is exponential in time and linear in space. We've already suggested that exponential algorithms are costly. In the case of Fibonacci, we didn't look for any other way of structuring the problem, but let's try to do better for Pascal. To do better, we have to go back to the original problem. A little information from combinatorics tells us that in actuality, Pascal's triangle is capturing the number of different ways of choosing a set of j objects from a set of n objects. This isn't obvious, by the way, so just accept it as a fact. Thus, the first element of a row is the number of ways of picking no objects, which is by definition 1. The last element of a row is the number of ways of picking a set of n objects from a set of n objects. Since the order in which we pick the objects doesn't matter, there's only one size n subset of a set of size n, hence this element is also 1. The general case is the number of different subsets of size j that can be created out of a set of size n. So what is that number? Well, we can pick the first element by selecting any of the n elements of the set. The second element has n minus 1 possibilities, and so on until we've picked out j objects. That product we can represent as a fraction of two factorial products, as you can see. Now, we're not quite done, because we said the order in which we pick the objects doesn't matter. Using the method we just described, we could pick the same set of j objects in j factorial different orderings. So to get the number of distinct subsets of size j, we factor this out, as shown. This leads to a straightforward way to compute Pascal. We can just rely on the factorial code we created earlier. Here we use factorial 3 times, once for the numerator and twice in the denominator. Notice how our procedural abstraction nicely isolates the details of fact from its use in this case, and the code here cleanly expresses the idea of computing Pascal based on factorial. So, do we do any better with this version of Pascal? Sure.
we know that this version of fact is linear. Our Pascal implementation uses fact 3 different times, but this is still linear in time. A similar analysis lets us also conclude that this is linear in space as well, because factorial is. While it might take 3 times as long to run than just running fact, what we're concerned with is the general order of growth, or how these processes' computational needs change with changing problem size, and both are linear in that change. Well, earlier we saw that there were different ways of computing factorial. Suppose we use the iterative version instead of the recursive one. The same effect takes place. Now we have a version of Pascal that is linear in time and constant in space, relying on the fact that factorial under this version is also linear in time and constant in space. Finally, if the use of an iterative factorial procedure gives us better performance, why not just do this computation directly as well? By that we mean just compute the 2 products, one for the numerator and one for the denominator, and save those extra multiplications that we're doing in the extra call to factorial. After all, we're just going to compute a product of terms that we know we're going to simply factor out later. We can do the same analysis for this version. Our help procedure is clearly constant in space and linear in time by the analysis we've done earlier. Our version of Pascal uses this twice, so while it does take less actual time than the previous version, it still has the same general behavior, linear in time and constant in space. Thus, in practical terms, this may be the best version, but theoretically it has the same class of behavior as our previous version. And this leads to our concluding point. First, we stress that the same problem may have many different solutions, and that these solutions may have different computational behaviors. Some problems are inherently exponential in nature. Others may have straightforward solutions that have exponential behavior, but often some additional thought can lead to more efficient solutions. Part of our goal is to get you to recognize different classes of behavior and to learn how to use the properties of standard algorithms to help you design efficient solutions to new problems.